Y, if you recall, the LHS of Nadal equation, it was by Q. The moment Y is increasing and Q is decreasing, Y is increasing and Q is decreasing, this factor is becoming higher, which we don't want. We have analyzed it in Nadal's equation. We want LHS to be as small as possible and RHS to be as high as possible. So LHS part जो है हमारा due to these oscillation gets affected. Now when these oscillations are affecting our LHS, we have to control these oscillations. तो कैसे कंट्रोल करते हैं उसके लिए डैम्पिंग है. विल सी, वो धीरे धीरे विल अंडरस्टैंड. फर्स्ट ऑफ ऑल, व्हाट काइंड ऑफ ऑसिलेशन हैपेंस? यू कैन सी the rolling stock is free to oscillate in all the three directions, X, Y and Z. X is what you call traction direction or longitudinal direction, you can say. Y is lateral direction in the same plane or horizontal plane, and Z is vertical oscillations in vertical direction. You can see here. This is the oscillation which is happening in longitudinal direction or traction direction. You can appreciate why such oscillations should happen during movement. ये क्यों होना चाहिए?
Sir, between and perfect connection between bogie and coach. Right.
So connection issue may be there. Buffers में कोई defect हो गया, coupler में कोई defect हो गया. Apart from that, operating feature also. Operating feature means when driver applies brake suddenly, or he gives pulls notches at once, many notches, or sometimes even due to track properties also, like gradients, steep gradients also, this can at steep gradients or junction of gradients also such vibration can get induced. Okay, so this is known as settling motion. Then in lateral direction, the oscillation happens. This is known as lurching. You can see why such motion should take place.
Alignment and gauge variations.
Right. Alignment and gauge, and it may also happen due to rolling stocks. में अगर rolling stock में भी कोई clearance आ गया in lateral direction beyond the tolerances, then also it will get induced. Then in Z direction, this movement is known as bouncing. And why this will happen? Again, due to unevenness of track or some defect in rolling stock which is restricting or dampening oscillation in vertical direction, maybe spring, maybe loose connection in vertical direction, all those things can happen. Okay. Class थोड़ा सा आधे घंटे बताओ कौन है? Now similarly in these three directions, rotation also, rotatory oscillation also takes place. If it is rotating about x-axis or longitudinal axis, that is known as rolling. You can see here. And you can appreciate why this should happen. When one of the rail is lower as compared to another rail. Either outer rail is lower or inner rail is lower. So that can create these rolling oscillations. Then about y-axis, pitching happens. Again, you can visualize this will happen when there is an unevenness in the track. Okay. And when it rotates or oscillates about z-axis, that is known as nodging. And why this should happen? Normally this will happen again due to alignment defects of the track. So these are possible oscillations in the rolling stock. Track defects, these are the reason. Similarly, rolling stock defects will also cause such oscillation. You can see that. Here you can see bouncing, pitching, rolling affects your dead load. It means it reduces or increases. Increase or reduction in Q is termed as on-loading or off-loading. So it can offload or on-load. And which one is more dangerous, on-loading or off-loading?
Sir, offloading.
Offloading.
Right. Similarly, nodging, lurching affects your Y value. Y means lateral value. And we want Y to be as low as possible. है कि नहीं? So these are the defects you can see. हमने ट्रैक का देख लिया था. Vehicle का we can see. Coupling में if defect is there, it will create you the oscillations related to shuttling or nodging. If worn wheel is there, it will cause hunting, nosing and lurching. Ineffective spring will cause again bouncing, pitching and rolling. Side bearer clearances issues are there. It will cause rolling and nosing oscillation, and ineffective pivot will again cause nosing action. So these are the oscillations and these are probable causes. So whenever something happens or some extra vibration is felt in your section, then please see both the properties of rolling stock as well as track. What might have induced such oscillation. And oscillations का ultimate effect यही है कि it is going to increase your lateral force and decrease the stabilizing force or downward force. Now we know that oscillation, whenever it happens, once we induce or induce some force in a system, it gets oscillated. But if suspension system is not there, it will come to standstill as per its natural frequency. And we know that in our rolling stock, we are providing a good suspension system. With this suspension system, we allow free oscillation of rolling stock. Now, free oscillation, when I say free oscillation, means oscillation as per its natural frequency. So this is allowed. This is as per the geometrical design of our rolling stock. We have allowed oscillations in the rolling stocks. And what is natural frequency? This is in case of a spring, you might have learned. Similarly, natural frequency means it is the frequency at which it will continue to oscillate. If it continue to oscillate, and similarly, if we induce forced vibration at such frequencies, जो natural frequency है, if we induce forced oscillation or forced oscillation at natural frequency, the amplitude will increase manifold. The amplitude of oscillation will increase manifold. So this is the natural frequency. Normally, if you vibrate anything, it will tend to oscillate as per its natural frequency. Okay. Natural frequency may be different in longitudinal direction, it may be different in lateral direction, it may be different in vertical direction. तीनों direction में अपना उसका natural frequency है, and accordingly whatever oscillation or forced oscillation you are giving to the rolling stock, it will depend upon the frequency of that forced oscillation either in longitudinal direction or in lateral direction or in vertical direction. If both matches natural frequency of rolling stock का say natural frequency FL is in lateral direction, F longitudinal is in longitudinal direction, and F vertical is in Z direction. So now the forced oscillation which we are creating, forced oscillation from track, how it will come? It may come due to unevenness defect. It may come due to alignment defect. Say if you have if our track is have unevenness. Track is at unevenness at every 13 meter or every weld, every fifth plate, say an unevenness of 1 mm or 2 mm, whatever it is. So what will happen? Our rolling stock, when it is moving, is subjected to a forced oscillation at every low joint. Similarly, if it is badly aligned, so at every joint, it will be subjected to some lateral oscillation. And if that lateral oscillation or if ये जो forcing की frequency है, if it matches to natural frequency of rolling stock, then oscillation takes place. So the same thing is explained in this slide. Say this is a simple case where in earlier track we used to provide fifth-plated joints, and at every 13 meter we used to get low joints due to hammering action at the joint. So if a rolling stock is moving at a speed of 13 meter per second, what will happen? This rolling stock will be subjected to a forced oscillation at every 1 second. Am I right? Now, if its speed increases, what will happen? The speed has increased to 26 meter per second. It will be subjected to a forced oscillation at every half second. Or we can say 2 cycles per second is the frequency of defect. Here we can see each second means 1 cycle per second is the frequency of defect which is which rolling stock is subjected to during the motion. अगर speed further बढ़ गया 39 meter per second हो गया, then the rolling stock will be subjected to forced oscillation at the rate of 3 Hz, 3 per second. ठीक है? Now if this 1 per second or 2 per second or 3 per second or 3 hertz you can say. If it is matches with the what you call natural frequency of this rolling stock, then wild oscillation will start taking place. At every low joint, the amplitude of oscillation will go on increasing little bit, and ultimately it may lead to a condition where amplitude is very high, or jumping or lateral direction there will be heavy jerks. So to avoid that, what we do, we try that whenever a new oscillation is induced at some place, let this the effect of this oscillation which has been induced in rolling stock gets dampened as early as possible. So for that purpose we provide dampening in the rolling stock. You must be aware, you must have seen, आपने coaches देखे ना, coaches या rolling stock otherwise goods के wagon देखे ना?
Yes, sir.
Yes, sir.
So do you recall dampeners are provided in rolling stocks? Do you recall?
Yes.
Yes, sir.
Yes, sir.
ICF पर क्या डैम्पनर था? ICF कोचेज में किस तरह के डैम्पनर थे? हाइड्रोलिक थे या स्प्रिंग के थ्रू था? स्प्रिंग कोई अदर एक्शन से था, फ्रिक्शन की वजह से था?
स्प्रिंग वाला था सर.
स्प्रिंग इज फॉर सस्पेंशन सिस्टम. डैम्पनर क्या था उसमें? डैम्पनर वाज हाइड्रोलिक पिस्टन्स, आपने देखे होंगे. हाइड्रोलिक, ठीक है ना, इस तरह के पिस्टन्स लगे हुए थे. दोज वेर द डैम्पनर्स. इफ यू रिकॉल दिस कैसनब कहाँ यूज होता है? वेयर वी यूज कैसनब होगी? इसमें कैसे सस्पेंस, इसमें कैसे डैम्पनिंग हो रही थी? फ्रिक्शन वेज, राइट. ठीक है. तो all these mechanisms, whatever you provide, are basically to retard or reduce the amplitude of oscillation before our rolling stock is subjected to next cycle of oscillation, maybe due to defect of track. ठीक है. This slide is clear. Why dampening is required?
Yes, sir.
Okay. If you don't provide dampening, what will happen? Say first induction of oscillation has happened here. If it is not controlled and again this vehicle is subjected to similar oscillation or due to track defect, the amplitude will increase and this will go on increasing. बढ़ता चला जाएगा. ठीक है ना? So that's why we reduce it by damping. Resonance हमने explain कर दिया. Same thing is written here. When the forcing frequency in a particular mode equals natural frequency in that mode, a phenomena called resonance occurs. Okay, means हमने जैसे दिया, say our rolling stock is moving at 39 meter per second. The track defect or track का जो low joints है, that is at every 13 meter. Means we are inducing frequency at the rate of 3 per second. Now if say rolling stock जो आपका चल रहा है, अलग अलग frequency है सबकी. Frequency is measured by RDSO. They oscillate the rolling stock and then they finally arrive at what is the rolling stock's natural frequency in lateral direction or longitudinal direction or vertical direction. They decide it. ठीक है ना? Whatever they say, if they say this the frequency is 3.5, so that becomes a standard information about that rolling stock. This rolling stock has a frequency of 3.5 in longitudinal direction, 2.5 in lateral direction or something in vertical direction. So these things are decided by RDSO. Now you are running a rolling stock which has frequency of 3 per second. Then this resonance phenomena will start, and to avoid this resonance phenomena we need to have dampener. So the same thing is explained here. If there is no damping in the system, the amplitude of oscillations at resonance tends to become infinite. The buildup of oscillation amplitude at the resonance can be controlled only by means of suitable dampening. The track defects when occurring in periodic form में जैसे बताया ना आपको, every 13 meter में you are facing some low joint. So that is periodic form of defect. At every gap of some time, rolling stock is subjected to some forced oscillation. So what kind of dampings are there? Under damping means if after initial excitation a few cycle of oscillations takes place before the system comes to rest at or equilibrium position, that is known as under damping. Over damping means system after being initially excited takes a long time, that is time more than one time period to come back to equilibrium. That is over damping. And critical damping means it will just prevent the system from overshooting the equilibrium position when displaced from it and released. It will happen immediately. You can see here. Critically damped. You can see first oscillation has first forced oscillation was applied here. Now second forced oscillation will come here. Before this, you can see the entire oscillation has been damped. This is critically damped, and this is the ideal condition. This should happen, but we cannot provide everywhere ideal damping. You can appreciate, because why? Because our forced oscillations are not fixed. Am I right?
Yes, sir.
Forced oscillation, it's not that it will happen at every 13 meter or every 26 meter or every 15 meter. It can happen anywhere in between. हो सकता है हर 10 मीटर पे मिल जाए, हो सकता है फर्स्ट 10 मीटर पे मिला, सेकंड 15 पे मिल जाए, थर्ड 5 मीटर पे मिल जाए. So we cannot make it critically damped. अगर critically damped करना है तो rolling stock should be ideal, track should be ideal, and then traction phenomena should be ideal. So ideal condition में only we can provide critically damped oscillation, critically damped, critical damping we can provide. Otherwise, whatever damping we provide, it will be critical for one situation only. Otherwise, for all other cases, it will generally become either undamped or overdamped or underdamped. Agar undamped hai, to you can see nothing is happening. The way it was oscillating, it is oscillating simply. You can see here. This is undamped case where we have done no damping. This black line, black solid line. No damping means it is not going to reduce. Whatever oscillation was placed here, it will continue to oscillate like this for infinite period. When it is critically damped, before entering into next oscillation or before completion of one time period, the entire effect of oscillation will go away. This is critical damping. Over damped, you can see. Over damped cases may it will lead to a situation when, despite giving forced oscillation, our rolling stock is not going to oscillate. It is going only. It is going to only shift from mean position. You can see an oscillation was applied, and now a disturbance was applied here. You can say a disturbance of this magnitude was applied. Now, as per normal जो simple harmonic motion concept है, जितना हमने इधर दिया, similar should have come here. But you can see in case of overdamped, it is not going to oscillate in other direction. It is going to restore its mean position, but it will take a long time. So fact ये है कि अगर आप overdamped कर दिए system को, then in that case it will not oscillate. It will only disturb from mean position, and then after a long gap of time, it will come back to mean position. That's all. So this also we don't want. What we want कि जैसे ही हमारा track rolling stock gets shifted towards one extreme, it should come back to center. Do you recall sinusoidal motion जो होता था track rolling stock का? Do you recall that? आपको याद है हमारा पर्पस? Whenever rolling stock comes this side, it should come to center. ऐसा चलता रहना चाहिए. But overdamped के केस में आप देख रहे हो कि जो oscillation एक बार हो गया, whatever disturbance has been created, it is not going to come to mean position immediately. It will take long time, और mean के बाद इस साइड तो बिल्कुल ही नहीं आएगा. मतलब कुछ इस तरह का हो जाता है. ऐसे आपने एक बार disturbance दे दिया तो ऐसे ही चलता रहेगा लंबे समय तक. Mean पे आते आते it will take long time, and this we don't want. ठीक है ना? So basically we want critically damped, but normally we should try कि under damped condition हमारा रहे. This is our requirement. ठीक है? Under damped में क्या होगा? Whatever disturbance you have applied, before getting next disturbance or next oscillation, amplitude has reduced drastically. That's all. That is our purpose. So this is related with the factor known as damping factor. Under damping, zeta से indicate किया, zeta is less than 1. Under damping, over damping greater than 1. Critical damping 1. So ideally we should try this, but normally ये position रहेगा, ठीक है? Zeta is actual damping by critical damping. Now here you can see what is the effect of zeta on amplitude magnification. If we are providing no zeta 0, what is happening? You can see amplitude is going towards infinity. And if you are providing zeta anywhere between, say, 0.6 के आसपास अगर आप देते हो तो amplitude starts reducing. First disturbance was 1 magnitude, you can see it is decreasing, and by 2.5 times or 3 times it is almost becoming 0. Okay, this is clear, the purpose of damping. If we don't provide damping, what will happen?
Yes,
amplitude will increase drastically. If we provide excessive dampening, then the rolling stock will take a significant time before coming to the mean position. But if we are providing damping anywhere between critical and under damping, our amplitude will reduce with time, and that's why it will not lead to excessive jerks during the motion. Okay, excessive jerks or excessive hunting, you can see that. The same thing what I explained in graph is written here. If zeta is 0, the magnification factor is infinite at resonance. In absence of damping, even a small irregularity, a small, we can say, periodic irregularity or cyclic irregularity, सिर्फ एक disturbance नहीं होगा. If disturbance is getting repeated, then in that case it would generate an infinite value of amplitude of oscillation in a vehicle. If zeta is adequate, say 0.7 or so, the magnification factor does not exceed 1, means it will start reducing before next disturbance or next forced oscillation is coming to the rolling stock. It will generally reduce, the amplitude will start reducing. Okay, so this was all about why do we provide damping, and if we don't provide it, what is going to happen. तो अगर आपके कभी किसी एक्सीडेंट साइट पे, डिरेलमेंट साइट में, इफ यू फाइंड दैट इन कैसनब के केस में मान लो उसका जो फ्रिक्शन वेज है वो गायब है, फ्रिक्शन वेज नहीं मिल रहा है, या पिस्टन्स में ऑयल होना चाहिए, हाइड्रोलिक ऑयल, व्हाट इज डैम्पनर के जो पिस्टन्स हैं उसमें हाइड्रोलिक ऑयल होना चाहिए, दैट इज नॉट देयर, देन यू कैन रिलेट दैट ड्यू टू ट्रैक डिफेक्ट्स encountered in past by the rolling stock, whatever forced oscillation, whatever oscillations has happened, it was not getting dampened as per design, and in turn it has led to excessive oscillation. And what is the effect of those oscillation? अगर excessive oscillation हो रहा है तो what is the effect on safe movement?
Lateral forces can increase.
Lateral forces will increase or Q will decrease. So in that way you can correlate it. ठीक है ना? So this concludes your free and forced oscillation. Now we'll see critical speed. Critical speed is normally not critical speed wala, just a minute. It's basically critical speed part is not very relevant for us. Us means field engineers. It is generally relevant for RDSO purpose, and that's why I have hidden it. But let me discuss little bit. थोड़ा discuss कर लेते हैं so that. It is a speed at the boundary condition between the stable and unstable condition is called as critical speed. Means once a rolling stock is subjected to the speed which is critical speed for that rolling stock, उसके बाद there will be vigorous hunting oscillation. And that's why whenever we introduce a new rolling stock on our system, we subject our, मान लो कोई rolling stock है, you are going to run at say 130 kmph. When we are introducing it on our system, we run it at about 140 to 145 kmph. Purpose is that we must see that if speed is increased, whether the rolling stock is going into the critical speed territory or not. Because at critical speed, hunting oscillations are very high. So we have to every time see whenever we are introducing any rolling stock, we run it not up to the maximum permitted speed only, we add about 10%. just to assess that whether we are running our rolling stock in near vicinity of critical speed or not. ठीक है? The speed at which lateral and vertical accelerations of vehicle body become severe and persist for some time, even for a couple of seconds, may be taken as critical speed. Accelerations are measured at vehicle floor as near to bogie pivot as possible. इसके लिए जैसे हम लोगों का वो होता है OMS होता है, उस तरह से इसके भी accelerometer होते हैं. Normally we keep it at vehicle floor or axle box level. The speed at which initial oscillations just maintains its amplitude is known as critical speed. Above critical speed, amplitude of small oscillations grows exponentially with time. Below critical speed, these amplitudes decay. These amplitude of oscillations, okay, decay. Instability sets in when speed of vehicle reaches its critical speed, and this part we ensure when we are introducing any rolling stock. जैसे कैसना बॉगी है, कैसना बॉगी का गुड स्टॉक है, से बॉक्सन. अब now we will run this boxen at say 100 kmph on track. So when we are introducing it, we will check it for 110-115 kmph, just to ensure that 100 kmph is not very near to critical speed. अगर बहुत ज्यादा hunting oscillation आने लगे, then we will understand that this has become a critical speed zone and we should keep speed lower than this. तो क्रिटिकल स्पीड अभी आप लोग को जरूरत नहीं है, जो लोग RDS वगैरह में काम करेंगे उनको जरूरत पड़ेगी. नॉर्मली क्रिटिकल स्पीड फील्ड वालों की जरूरत नहीं भाई, बिकॉज if critical speed is 120, we keep our rolling stock at about 100 or 105. So that's why this part does not comes in picture. ठीक है, बट कभी ओवर स्पीडिंग का केस हो गया, then you can correlate it. That much help you can take. Now the last part is lateral track stability. अभी तक whatever we have learned in rail wheel interaction, what we have assumed that forces are coming on track and track is acting as a rigid member. Is it right or not? Am I right? ठीक है. But Prudhomme established that track is also not stable beyond certain limit, and that's what he has indicated in his formula. You can see. These three things can happen. Either rail can slip little bit, or it can bend little bit, or there may be some torsion. So these things can happen if excessive lateral forces are coming, and Prudhomme established that under any case the lateral force on an average good track should fulfill this criteria. Whenever we are introducing a rolling stock, we have to see that lateral forces which are coming on our track should not increase this value. This is known as Prudhomme's formula. P is axle load. Okay, so now if you are running a 20-ton axle load, lateral force should not increase 0.85 into 1 plus 20/3, which will come around say 6 टन के आसपास आएगा. अगर इससे ज्यादा lateral force आ गया, then that rolling stock will not be passed. So this is again useful for introduction of rolling stock. जब आप नया लेते हो उस समय we measure it. इसका measurement होता है, ठीक है ना. Rolling stock को वो हम लोग करते हैं, instrumentation करते हैं, and then we measure lateral forces. But of course this lateral forces we don't measure at wheel level. यहाँ नहीं करते हम लोग, जैसे ट्रैक we measure it at axle box level here. We are unable to measure here. Of course, now we are in the process of purchase of measuring wheel on Indian Railway. If measuring wheel will be purchased, then we can come to know actual force which the rolling stock will transfer to our track. That we can assure. But right now we are measuring at axle box level. Okay. So these were three parts which were missing. Any questions? आज के क्लास में या पहले वाले क्लास में भी कोई क्वेश्चन हो तो पूछ सकते हो. हाँ जी, Do you have any questions in today's class or the earlier two classes?
No, sir.
No?
No, sir.
Okay, so I am concluding now. The purpose